Everything around us, from the smallest grain of sand to the largest star, is made up of tiny particles called atoms. These atoms are the building blocks of all matter, forming the diverse substances we encounter in our daily lives. But atoms themselves are made up of even smaller particles, called subatomic particles. These include protons, neutrons, and electrons, each playing a crucial role in the structure and behavior of atoms. These subatomic particles are the fundamental building blocks of all matter in the universe. They combine in various ways to create the elements and compounds that make up everything we see and touch. For many years, scientists have been trying to understand what these particles are and how they interact with each other. Through experiments and observations, they have uncovered the complex interactions that govern the behavior of matter at the smallest scales. This quest has led to the development of a theory called the Standard Model of Particle Physics, which describes the fundamental forces of nature and the particles that carry them. The Standard Model explains how particles interact through forces like electromagnetism, the strong nuclear force, and the weak nuclear force. The Standard Model is a remarkable achievement in physics, but it has always had one glaring omission. It couldn't explain why some particles have mass while others do not. This limitation puzzled scientists for decades, as understanding mass is crucial to comprehending the universe's structure. This is where the Higgs boson comes in. The discovery of the Higgs boson provided the missing piece of the puzzle, explaining how particles acquire mass through their interaction with the Higgs field, a fundamental aspect of our universe. Mass is a fundamental property of matter. It determines how much an object resists acceleration when a force is applied to it. For example, it takes more force to push a heavy car than a light one. But what gives particles mass? Why do some particles, like protons and neutrons, have mass, while others, like photons, particles of light, have no mass at all? This was a question that puzzled physicists for decades. In the 1960s, a group of physicists, including Peter Higgs, Francois Englert, and Robert Brout, proposed a revolutionary idea. They suggested that the universe is permeated by an invisible field, now known as the Higgs field. Imagine the Higgs field as a kind of cosmic molasses that fills all of space. Just as it's harder to move through molasses than through air, particles that interact strongly with the Higgs field experience more resistance and therefore have more mass. Particles that interact weakly with the Higgs field have less mass, and particles that don't interact with the Higgs field at all, like photons, have no mass. This idea was a major breakthrough in particle physics. It provided a way to explain why particles have mass without violating any of the fundamental laws of physics. But there was a problem. The Higgs field was purely theoretical. No one had ever detected it, and no one knew if it really existed. To prove the existence of the Higgs field, physicists needed to find its associated particle, the Higgs boson. Just as a ripple in a pond indicates the presence of water, the Higgs boson is a quantum excitation of the Higgs field. Detecting the Higgs boson would provide the evidence needed to confirm the existence of the Higgs field and validate the theory behind it. However, finding the Higgs boson was no easy task. It is an extremely rare and short-lived particle, and it can only be created in high-energy collisions, like those that occur in particle accelerators. Section 5. The Standard Model of Particle Physics. The Standard Model of Particle Physics is the best theory we have to explain the fundamental building blocks of matter and the forces that govern them. It describes a set of fundamental particles, including quarks, leptons, and bosons, and their interactions through the electromagnetic, weak, and strong forces. The Higgs boson is a crucial missing piece of this model, responsible for giving mass to other particles. The discovery of the Higgs boson would complete the Standard Model and provide a more comprehensive understanding of the universe at its most fundamental level. It would also open up new avenues of research in particle physics and cosmology. Section 6. The Hunt for the God Particle. The search for the Higgs boson, often referred to as the God particle, was a monumental global effort. It involved thousands of scientists from all over the world, each contributing their expertise and knowledge to this grand quest. For decades, physicists had been building increasingly powerful particle accelerators, hoping to create the elusive particle in the laboratory. These machines were marvels of engineering, designed to recreate the conditions just moments after the Big Bang. The Large Electron Positron Collider, or LEP, at CERN, the European Organization for Nuclear Research, was one such machine that played a crucial role in narrowing down the possible mass range of the Higgs boson. It was a significant step forward in the journey to uncover the mysteries of the universe. However, it was the Large Hadron Collider, or LHC, also located at CERN, that would ultimately lead to the groundbreaking discovery. The LHC was a technological marvel, representing the pinnacle of human ingenuity and scientific collaboration. The LHC is the world's largest and most powerful particle accelerator, capable of colliding protons at nearly the speed of light. These collisions created conditions similar to those just after the Big Bang, providing a unique opportunity to observe the Higgs boson. With its unprecedented energy levels, the LHC provided the best chance yet of producing and detecting the Higgs boson. Scientists meticulously analyzed the data from countless collisions, searching for the telltale signs of the particle that would confirm the existence of the Higgs field, a fundamental component of our understanding of the universe. Section 7. The Large Hadron Collider, a marvel of modern science. The Large Hadron Collider is an engineering marvel, a testament to human ingenuity and collaboration. It represents the pinnacle of modern physics and engineering, bringing together thousands of scientists and engineers from around the world. It consists of a 27-kilometer ring of superconducting magnets buried 100 meters underground near Geneva, Switzerland. These magnets are cooled to temperatures colder than outer space to maintain their superconducting state. Inside the ring, two beams of protons travel in opposite directions at close to the speed of light, guided by powerful magnets. These protons are accelerated to such high speeds that they complete over 11,000 laps of the ring every second. At specific points along the ring, these beams are brought to collide head-on, creating incredibly energetic explosions that mimic the conditions of the early universe. These collisions generate temperatures and energy densities similar to those just moments after the Big Bang. Sophisticated detectors, such as ATLAS and CMS, are positioned around the collision points to track and measure the properties of the particles produced in these collisions. These detectors are some of the most advanced scientific instruments ever built. These detectors are essential for identifying the signature of the Higgs boson amidst the debris of other particles created in the high-energy collisions. The discovery of the Higgs boson in 2012 was a monumental achievement, confirming a key part of the standard model of particle physics. Section 8, 2012, A Year of Discovery. On July 4, 2012, after years of anticipation and meticulous analysis of data from the LHC, physicists at CERN announced the discovery of a new particle with properties consistent with those predicted for the Higgs boson. This announcement sent shockwaves through the scientific community and beyond, marking a historic moment in our understanding of the universe. The discovery was the culmination of decades of theoretical and experimental work, a testament to the power of human curiosity and collaboration. It was a victory for the standard model of particle physics and a major step forward in our quest to unravel the mysteries of the universe. Section 9. The God particle, more than just a nickname. The Higgs boson is often referred to as the God particle, a nickname that has sparked controversy and debate. The nickname originated from the title of Leon Lederman's book, The God Particle. If the universe is the answer, what is the question? However, the term God particle has been met with mixed reactions, with some physicists embracing it as a catchy moniker, while others criticize it as being misleading and sensationalized. Regardless of the nickname, the discovery of the Higgs boson is a testament to the power of the scientific method, a process of observation, experimentation, and reasoning that has allowed us to probe the deepest secrets of the universe. Section 10. Understanding our universe. The discovery of the Higgs boson has profound implications for our understanding of the universe. It confirms the existence of the Higgs field, a fundamental aspect of reality that permeates all of space and gives mass to other particles. This understanding helps us explain why particles have mass and why the universe is the way it is. Moreover, the Higgs boson plays a crucial role in cosmology, the study of the origin and evolution of the universe. It helps us understand the conditions in the very early universe, fractions of a second after the Big Bang, when the fundamental forces of nature were still unified. Section 11. The future of physics beyond the Higgs. While the discovery of the Higgs boson was a monumental achievement, it is by no means the end of the story. In fact, it marks the beginning of a new chapter in particle physics. Physicists are now using the LHC and other experiments to study the properties of the Higgs boson in more detail, hoping to uncover new physics beyond the standard model. The search for new particles and forces is ongoing, and the Higgs boson serves as a valuable tool in this quest. Its discovery has opened up new avenues of research, with the potential to revolutionize our understanding of the universe and our place in it.